3.2, and we started discussing this dot point in 3.1. However, we formalized it in this body of text. So describe the difference between conductors, insulators, and semiconductors in terms of their band structures and relative electrical resistance. Okay, so the main thing here is to highlight what is in the box on the right hand side with the pronounced gaps in each of those scenarios in conductors, insulators, and semiconductors. You can see by those gaps, such as in the conductors, that they are touching, and in semiconductors the gap is very minimum. However, in insulators, the middle diagram there, you can see the forbidden gap energy is larger. So where did this all come from? It came from the band theory and has been developed to explain the difference in conductivity of conductors, semiconductors, and insulators. This idea is that the electrons in the outermost shell occupied level of atoms, the valence electrons, are said to be in the valence band, as mentioned in 3.1. The energy levels above this level are considered to be in the conduction band. The difference in conductivity depends on the value of the energy gap between those two bands, and we've discussed that in the diagram on the right hand side. So in a conductor, the conduction and the valence band overlap. This allows the valence electrons to easily move along into the conduction band, giving the material low electrical resistance. In insulators, there is a large forbidden energy band, which makes it difficult for the valence electrons to move into the conduction band, giving the material a high electrical resistance. In semiconductors, it is between both the conductor and the insulator. So the forbidden energy band is not too wide. Under certain conditions, electrons in the valence band can gain sufficient energy to cross the gap. This reduces the electrical resistance of the material.